Hello everyone. Today we're going to start off talking about section 2.1, which are functions. Okay, a few definitions here. A function is defined that every element of the domain, which includes the x values, has exactly one element of the range, which are the y values. Okay, the x values, we're going to call those a few different things. Sometimes we're going to call them the input of the function. They will also be called the independent variable, while y values will be called the output or the dependent variable. All right. A few different ways you can see a function represented. One way is by mapping, which basically takes these inputs over here on the left and maps them or connects them to an output on the right. So you can see here at the top, all the inputs are being mapped to exactly one output. So that's all good. Don't let the bottom here trip you up. Even though the chicken sandwich and the McDonald's McChicken are both being mapped to the 23, these two inputs only have one output. So that's perfectly fine. What you can't see is one of these inputs, like the Burger King chicken sandwich, have two outputs. That would make it not a function. But the way this mapping situation is written, this is a function. Okay, for the ordered pairs, again, making sure every x has exactly one y. The problem down here is with those 2 points, 5 can't spit out a 3 and then spit out a 4. So this is not a function. All right. So the reason I said spit out a 3 and spit out a 4 is because when I think about functions, I always think about this function machine. It's a very elementary picture, but it's going to help us, especially when we start doing composite functions later on. Basically, have an input, gets down here into this function, gets crunched up and processed, and then an output is spit out. Okay, that thought process helps us make sense why it can only have one output, and that's going to help us later on, like I said. All right, let's talk about our mathematical language here. So when you see f parentheses x, that does not mean f times x. In algebra, a lot of times parentheses mean multiplication. But here it simply is a way to write and denote a function. So f of x is what that says. So when we get down here and see f of 4, what that wants us to do is go to the function called f and plug in a 4 everywhere we see an x. So f of 4 is going to look like 2 times 4 squared minus 3 times 4. I just replaced these two x's with 4's. From there, you clean it up as far as you can. So combine like terms, follow your order of operations. I have to square first, so I get 16 minus 12. So f of 4, 2 times 16 is 32, minus 12 is 20. So f of 4 is 20. Over here, f of x plus 3 is the same thing. A little different though. I have to plug in x plus 3 everywhere I see an x. So when I do that, here's the original function, right? 2 times something squared minus 3 times something. In the original function, those blanks here are x's. I want them now to be x plus 3's. So I'm replacing these x's up here with an x plus 3 and an x plus 3. And then the process there is kind of the same as the last one. It's going to be a little different here because I won't have a numeric answer. I have to do parentheses and exponents first. Exponents are before parentheses in this one. So what I have to do here is take this x plus 3. Be careful, x plus 3 squared is really x plus 3 times x plus 3. So I've got to FOIL that out. I can't take that exponent and distribute it. There is no distributing of an exponent. So x plus 3 times x plus 3 is x squared plus 6x plus 9. And then here, there's a second piece of it. I have to take that 3, and it's actually a negative 3, and distribute it into both of these. So negative 3 times x is negative 3x, and then minus 9. All right. Now take this 2, distribute it in, 2x squared plus 12x plus 18, and then minus 3x minus 9. And if I combine all my like terms, f of x plus 3 is 2x squared plus 9x plus 9. Okay, there we go. Now this one over here is a little strange. I've already plugged in x everywhere. This is what I have up here, so that doesn't affect anything. But what this really basically wants me to do is take the function f of x, right, and multiply it by a negative out front. Basically make it multiply it by -1. So what this is going to turn into is just a negative out in front of 2x squared minus 3x, right? Let's put in a negative. If I go up here, it's supposed to put a negative on both sides of the equation. So when I clean this up, all I have to do is strip the negative, and it's negative 2x squared plus 3x, negative f of x. All right. So using our mathematical notation there to clean some things up. Now let's try this one. This one is an important one. It's called the difference quotient, and it's a famous quotient you'll learn in your first days of calculus. But using the same function from above, 2x squared minus 3x. All right, I'll write that down. Okay, we want to find the difference quotient. So this is just two or three pieces in one. This first thing is telling me, like we did in the last problem, to take x plus h and plug it in everywhere I see an x. So this is going to be 2 instead of an x. I'm putting x plus h minus a 3 and an x plus h. Again, all I did was I replaced these x's with x plus h and x plus h. All right. Now I'm going to color code this. Second piece minus, this was the first piece, now I'm doing the second piece. This just wants me to subtract f of x. So f of x is what's up here, so I have to take that whole thing, 2x squared minus 3x, and just put it there. But because I want to subtract the whole function, I've got to put parentheses around that. I have to distribute this negative in to that function. And then that's going to be divided by, let's do this in black, divided by h. There's nothing I can do with that h. All right, so let's start cleaning this up. Just like I did before, I have to FOIL the x plus h. So it's going to be x plus h times x plus h, and that's just a FOIL. So it's 2. Once you FOIL x plus h times x plus h, you get x squared plus 2hx plus h squared, right? It's a little strange, but you get some h's in there. Those h's work just like numbers. And then minus 3, I'm going to distribute this negative 3 in just like I did in the last problem. Negative 3x minus 3h. In red, I'm going to distribute the negative in. So this is negative 2x squared plus 3x. And this is all over h still. All right. So this isn't technically really a hard problem. This is just a little bit of work. Now up here, I'm going to distribute this 2 into everything all the way through. So I get 2x squared plus 4hx plus 2h squared. Then minus 3x minus 3h. And I still have I'm going to keep everything blue now, minus 2x squared plus 3x all over h. All right. Let's combine some like terms up top. Now, if you're doing this problem correctly, at this step, you're going to see a lot of things reduced to 0. 2x squared minus 2x squared, that's 0. Minus 3x plus 3x is 0. So all I have left is a 4hx plus 2, let's go in this order. Well, I'm going to keep it in that order. Plus 2h squared minus 3h all over h. Okay? Now, if you've done it correctly up to this point, every time you do a difference quotient problem, these h's, you should have an h in every term up top of the numerator and an h in the denominator. If you remember from Algebra 2 or from college algebra, if you have a factor everywhere up top and everywhere down low, that can reduce. So that h is all going to go away. One of those is going to stay. And what I have for a final answer is 4x plus 2h minus 3. All right. That is how we manipulate that problem. Okay, we're not going to do another one like that. You guys can practice that one on your own. It's going to be the same procedure each time. Okay, let's talk quickly about interval notation. You guys all should have seen this. Interval notation is a technique to describe an interval of numbers in a concise way. So if we want to describe all the numbers between 2 and 5, including 2 and including 5, if we want to include the endpoints, we use a bracket. So 2, we use the leftmost number first, comma, and then all the way to 5. And then because 5 is included, we use a bracket. So what this stands for, this 2, 5 with brackets, is All of the numbers between 2 and 5, including 2, including 5. Okay, now if we go all the way to the left like this, oh, sorry, I don't want that. If we go all the way to the left like this, the left point is actually negative infinity. So negative infinity, infinities will always have a parenthesis because you can never get there and touch it. Infinity up to 5, we want it, that's all these numbers. Because 5 is not included, it's a parenthesis. So if you want to include the endpoint, it's a bracket. If you do not want to include it, it's a parenthesis. If we have two intervals we want to include, so this first one is negative infinity to 2, parenthesis on the infinity, parenthesis on the 2. If you want to combine these two, we do a union, and then parenthesis 5 to infinity. So interval notation, you guys have all seen it before. It's a quick way to describe a huge interval of numbers. Parentheses, brackets, always the left endpoint, comma, right endpoint. All right, so that's what we're going to start doing with domain here. Okay, we want to find the domain of the following problem. Now there's three red flags we have to watch out for with domain. Okay, starting off, we're going to look at what is the domain of all real numbers. So if you don't see anything else, so right away at the beginning of the problem, if you don't see anything, you can start with the domain being all real numbers. Okay, now two red flags. If the equation has a denominator, the denominator, you must exclude anything that makes a 0 in the denominator. So that's red flag number 1. If the equation has a radical of even index, the radical is the number right here in a root, right? So if you have a square root, or if you have a fourth root, or if you have a sixth root, you can't have the radical can't be negative. So the thing underneath the radical must be positive. Okay? All right. So let's look at the domain of this first one. We have x plus 4 over x squared minus 2x minus 3. There's no square roots or fourth roots here, but we do have a denominator. All right, so this denominator here, x squared minus 2x minus 3, cannot be 0. So all we're going to do is say, okay, take this denominator over here and say x squared minus 2x minus 3. You cannot be 0. Now, solving this on the left side, you guys have done a ton. It's factorable, so you can do x minus 3. X plus 1 cannot equal 0, which means x cannot equal 3 or negative 1. Those are my restrictions. All right. Now, when I ask you to do set notation, the interval and set notation, sometimes one's better, sometimes the other. That's why we're practicing both. So you start off with this funky bracket. That means the values of x, the straight line means such that, and then x, you can write the restrictions here. So the values of x such that x cannot be 3 or negative 1. And you do another little curly Q bracket, and that's set notation. Sometimes that's better, sometimes it's not. The interval notation, for this one, we have to think about the interval of numbers, right? If we have a number line, we start with all real numbers. The only things it can't be, that the x can't be, is negative 1 and 3. So basically you have open intervals there, but you're allowed to be everything else on that number line. All right, so this number line here I'm drawing is optional. It is helpful sometimes to visualize it. If you miss this middle piece sometimes, think about this number line. But my interval notation here is negative infinity to negative 1, parentheses on everything, union, negative 1 to 3, that little piece in the middle, that little interval in the middle, union, 3 to infinity. All right, let's get another one. Here, we have a radical, square root, right? So really when you see a radical and there's nothing there, the index is 2. So this guy can't be 0, we said, or it has to be positive. So what we're going to do is take 3 minus 2x. Another way to say that it has to be positive is that it has to be greater than or equal to 0. So those are basically the two big setups. Denominators, we're going to say can't equal 0. Radicals with even index, we'll say have to be greater than or equal to 0. All right? In general, that's what's going to happen most times. So start cleaning this up. Subtract 3 to both sides, minus 3. And we're going to divide by negative 2. Now be careful. There's a rule that when you divide an inequality by a negative, you have to flip the direction of the inequality. So less than or equal to 3 halves. All right. So my set notation, we'll do that first. Values of x such that x, and now we just put the restriction. It has to be less than or equal to 3 halves. Another curly Q bracket. Okay, interval notation for this one. If you think about the number line being all real numbers, here's 3/2. We have to be less than or equal to that number, so we're going that way. So we're negative infinity, comma, 3/2 with a bracket. All right. Let's look at these two. So letter C, looking back at my red flags. I have a denominator here technically over 1, but it doesn't have any variables in it, so that can never be 0. So I don't have a denominator to worry about. I don't have any square roots or fourth roots. I have an x squared, but x squared is not a radical. So because this has no red flags, my domain for this is all real numbers. All right. Now, another way to think about this is the graph of x squared minus 9. If you guys remember that graph, that's a parabola shifted down 9 units. So you can kind of verify your thinking. And if you look at the domain of that graph moving left to right, there are no restrictions. So that's why it's all real numbers. Okay, letter D. This is kind of a combo. We do have a denominator, so we're thinking that x cannot be 0, but we also have a radical, a square root. So let's go back to this last one we did. With the radical, we said anything under the square root has to be greater than or equal to 0. So we take that 5 minus x and say you're greater than or equal to 0. That's a good first step. But here's where it's different. Because this 5 minus x is also in the denominator, it can't equal 0. So all I have to do is change this inequality to a greater than, right? And now I solve. Subtract 5 to both sides. Divide both sides by -1 while I flip the direction of the inequality. So x must be less than 5. Okay? So all I want is interval notation for this one. So at less than 5, I'll draw my little number line just so we can see it. Here's 5. I want everything to the left. Again, that number line's optional, especially if you're getting all these right. So negative infinity to 5, parenthesis. All right, I'm going to pause this video here. Be sure to watch the second video and then try the homework.